All right, folks, here we go. Contextual problems with scaling areas. Fun stuff. So we're going to look at solving for scale factor in context. Okay, so some contextual problems. And we're going to find missing dimensions. And we're going to scale areas in context. And we're going to have fun. I think there might even be a little rate problem that sneaks in at the end. So in order to increase the visibility, so this is solving for scale factor, of construction signs in the TCH, the Department of Highways wants to increase the visible area of each sign by 60%. What scale factor is required? Okay, so if we want to increase the visible area by 60%, we want the image, or the new guy, to have 60% greater than the original, or the actual one that we start with. So if we're scaling up by 60%, we're going to be 160% of what we used to be. And that means it's 1.6 multiplied by what it used to be. That's how that works. Okay, so if I'm going to take 1.6, remember the area of the image over the area of the actual. If we divide both sides by the area of the actual here, that's what we've got, and that's 1.6, but that has to be equal to k squared according to our formula. So k squared is equal to 1.6. So to get a value for k, I'd have to take the square root of that. Don't like decimals, but sometimes we don't really have much choice. All right, so we've got 1.265 roughly. So our scale factor here is about 1.265. Okay, so we'd have to multiply all the dimensions by this to increase the area by 60%. A local drive-through coffee shop we're finding missing dimensions in context. Okay, so I don't know, missing dimensions, close encounters of the third kind or something here. A local drive-through coffee shop sells advertising space on the wall of its building that faces the drive-through. The wall space is 9 feet high, so I'm going to assume it's a rectangular wall, and it's 9 feet high. Okay. An advertiser claims that if she doubles the area of her sign, that is 6 feet high, it'll still fit on the wall. Well, you might be suspicious with that, because intuitively we would think that if we double 6 feet, we're going to get 12, and that ain't going to fit on a 9-foot wall. But let's see what actually happens. So we want to double the area of the sign. So the area of the image is going to be twice the area of the original, or the actual one that we started with. That's what doubling means. So the area of the image over the area of the actual is going to equal 2, but that also has to be equal to k squared, squared scale factor. So we've got k squared equals 2, which means that k is going to be the square root of 2, which when I went to school was about 1.414. Okay, so if that's the case, the linear scale factor is 1.414. So if I take my 6 feet, which was the old height, and I multiply that by 1.414, well, I'm not going to get 12 feet. I'm going to get 6 times 1.414 is only 8.484. So I'm going to say it's about 8.5 feet. What? It sure is, and not only that, but it will fit on your 9-foot wall. Very clever lady, this advertiser. Example 3. Scaling areas in context. A 1 to 120th scale model is used to determine the cost of mowing a municipal park. The contractor charges 80 cents per square meter to mow the area of the park. I hope that's what they charge for the whole season. That's very expensive. So let's assume this is for a whole year. If the model measures 1.5 meters by 3 meters, the one they're using to figure out the cost, how much will the mowing cost? Okay, let's see. So the model has an area. So this is the area of the image, because that's the model, right? That's going to be 1.5 times 3. And 1.5 threes is 4.5. That's 4.5 square meters. That's the area of the image. So let's figure out what the area of the park is, and then we just use a rate over here to figure out how much it's going to cost. Okay, so area of the image is going to be equal to k squared times the area of the actual. So as we said before, if we want to get the area of the actual, we have to divide by k squared. So we take the area of the actual thing we're after here, is going to be the area of the image, divided by k squared. So that is 4.5 meters squared, divided by, now k is 1 over 120, and then we got to square that. So we're going to end up multiplying by 120 squared because we're dividing by the scale factor, which is a fraction. So we're going to end up with 4.5 times 120 squared, which is 64,800. That's a huge park. So we've got 64,800 meters squared to be mowed. So let's figure out the cost then using the rate that they quoted. So the cost is the rate, which is $1. No, sorry, it's less than $1. It's 80 cents per meter squared, multiplied by the area of the park, which is 64,800 meters squared. So 80% of that, so 0.8 times 64,800 gives us a total cost of $51,840. I hope that's once every 10 years. That's a lot of money. $51,840 to take care of the cost of mowing the municipal park for the year. Not cheap stuff. Quick summary of all the things we've looked at here. So we sort of learned all this stuff by example because we're into contextual problems now. So to quickly find a scale factor for known areas, use the formula or just divide the areas and take the square root of the ratio. To find a missing dimension, determine the scale factor first if you don't have it, then multiply if the dimension is on the model, or if you want to find one that's on the actual object, we divide. We just saw that. And the area of an actual object can be found by dividing the area of the scale model or the diagram by the square of the scale factor. Hope that helps.